Hello, this is Richard Hammock's Calculus 1. We are going to wrap this course up in the next two lectures, lectures 45A and 45B. In lecture 45A, we'll talk about other integration techniques. Most recently, we've been talking about the integration technique of substitution. And it's been highly effective, but it doesn't always work. We're going to start out today with the question, what to do if substitution doesn't work? You'll recall that for substitution to work, the integral that you're trying to find must have a very special form. It must have the form of the integral of f of g of x, g prime of x, dx, or can be put into that form. And if that's the case, you can make a substitution, u equals g of x, and doing so, du will be equal to g prime of x dx. And with that substitution, this turns into a much simpler integral, the integral of f of u du. And of course, it's vitally important that we be able to evaluate that integral to find it. So for substitution to work, a lot has to fall into place. But when it does, we can get an easy answer. For example, think of the integral of sine squared x cosine x dx. When you look at that with your experience with substitution, you probably immediately see to make the substitution u equals sine of x. And doing so, du dx will be cosine of x. So du is cosine x dx. So this cosine x dx in the integral equals du. And the thing that we're squaring here is sine of x, which is u. So this integral becomes the integral of u squared du, a very simple integral. That's our integral of f of u du in this case. And we could do it with the power rule for integration. And plugging the u equals sine of x back in there, we get an answer of sine cubed x over 3 plus c. It was very effective, this method of substitution, for this problem. But imagine you had a slightly different integral. The same thing except that it doesn't have the cosine of x. Here, the integral is the integral of sine squared x dx. Now looking at that, if you made a substitution u equals sine of x as you did up here, then du would be cosine x dx, but you don't have a cosine x dx. All you have is a dx here. So you don't have a match. So substitution fails in this case. And you could try other things and you'd be hard pressed to find this integral, most likely. Likewise, think of the integral of cosine x cubed, 3x cubed dx. Well, here you look at that and you'd see, let's make a substitution of u equals x cubed. Fine. But doing that, you would get du is 3x squared dx, and that doesn't match what you have in the integral. You have 3x cubed dx. So substitution here doesn't quite work. You don't get a match for du. And you can try other methods with this, but this integral is going to be problematic. Substitution just doesn't work. For that matter, think of the integral of secant x dx. That's a really simple integral, but we have no means of evaluating it. Or the integral of ln of x dx. We don't have a rule for that, and substitution's not going to work here. So you can find lots of integrals that you can't do at this point. Substitution doesn't work for them, and our other techniques don't work for them either. So what do you do in this case? Well, the most immediate answer is to wait until Calculus 2. You'll be able to do these and many, many other types of integrals after taking Calculus 2. So what to do if substitution doesn't work? A big answer is take Calculus 2. But there are some techniques available to us now in Calc 1 that we can apply, and I want to talk about those today. We'll start with the idea of using trig identities. Think about the integral from the previous slide that we couldn't do, the integral of sine squared x dx. What is it? Substitution didn't work. And here's another one, the integral of cosine squared x dx. And you'll find that substitution doesn't work for it either. For these two integrals, one thing that does work is a trig identity. Think way back to part 1 of this course when we were talking about trig identities. One of them was sine squared x equals 1 minus cosine 2x over 2. This came from the double angle formula for cosine. And I mentioned at the time that its importance is that it replaces the sine squared x with an expression that doesn't have a square. It's a power of 1. And I said that's going to be useful. And we've come to the point at which it is useful because it was precisely this square that was giving us the trouble. If it wasn't there, we could do this integral. Likewise, for the integral of cosine squared x dx, you can use the identity cosine squared x equals 1 plus cosine 2x over 2. Let's try this. Let's take the integral of cosine squared x dx. Substitution doesn't work, but we'll try replacing the cosine squared x with this expression that it's equal to. So we get the integral of 1 plus cosine 2x over 2 dx, and let's factor out a 1/2, so we get 1/2 integral of 1 plus cosine 2x dx. And look at this. We can certainly take the integral of 1, it's x, and also we can do the integral of cosine 2x. You can do that with substitution or just do it in your head. Doing this integral, we have the 1/2 out in front. The integral of 1 is x, and the integral of cosine 2x is 1/2 sine of 2x, and then we add a c. So there's our answer. Simplifying a little bit, x over 2 plus 1/4 sine 2x plus c. So even though substitution didn't work, we could solve this one with a trig identity. And very quickly, let's check our work. Let's take the derivative of this answer. If we did it right, it's going to give us cosine squared x. So the derivative of x over 2 is 1/2. The derivative of 1/4 sine 2x is by the chain rule 1/4 cosine 2x times 2. That simplifies to 1 plus cosine 2x over 2. Well, does that equal cosine squared x? Actually, our identity says yes, it does. So we get cosine squared x. That's the integrand. So it checks back. We did the work correctly. You'll find, especially if you go on to Calc 2 and Calc 3, that you use a lot of these identities. And they're available to us now here in Calculus 1, so be on the lookout for them, or opportunities to use them. We'll move on to another integration technique. Every once in a while, you can use a property of even or odd functions to find a definite integral. It doesn't always work, but when it does, it's really useful. Remember from your algebra course maybe years ago, you studied even and odd functions. A function f of x is even if f of minus x equals f of x for all x in its domain. So for instance, here's a picture of an even function. If you take f of x for this x, that's equal to what you would get if you took negative x on the other side and f of that. F of minus x equals f of x. So this is an even function. Examples of even functions include f of x equals x squared, which is the function I've graphed here. Polynomials where every degree of x is even. F of x equals cosine x is an even function because one of our trig identities says cosine of minus x equals cosine of x. That makes it even. And there are many other even functions. You'll remember also that a function f is odd if f of minus x equals negative f of x for all x in its domain. So here's a picture of an odd function. Here's an x. You look at f of x. It's up here. Now go to the other side to minus x and take f of minus x. And in this picture, f of minus x is negative of f of x. So this property holds for the function pictured here. So that's an odd function. Odd functions are symmetric with respect to the origin. Examples of odd functions include f of x equals x cubed, which is shown here. Polynomials where every power is odd. And sine of x is an odd function because you know that sine of negative x equals negative sine of x. And there are many other examples of odd functions. I've just listed 3 of them here. Now, of course, most functions are neither even nor odd. These are just special properties that some functions may possess. But when a function is even or odd, you get some special formulas involving integrals of those functions, or definite integrals. And here's one. For even functions f of x, if you have the integral from negative a to a f of x dx, where the lower limit of integration is the negative of the upper limit of integration, it's pretty easy to see that's equal to 2 times the integral from 0 to a f of x dx. Because if you think about a up minus a down, in this case everything is a up in this picture, so it's a good illustration. The integral from 0 to a f of x would be this area right here, which is half of the total area between negative a and a. So if you double that, this area plus this one, you get the integral from negative a to f of x dx. Now this formula is not terribly useful, admittedly, because if you're having trouble working out this definite integral, the f of x would be problematic. You're probably going to have the same problem over here. But the situation for odd functions is different, and it's really useful. If f of x is odd, then the integral from negative a to a f of x dx, you can say definitively it equals 0. That's going to be your answer. And the reason is that in an odd function, your a up and your a down, they're going to cancel each other out, as shown here. So this formula gives an answer for certain integrals. Now, admittedly, the limits of integration have to be really special. The one on the bottom has to be the negative of the one on the top, and the function f has to be odd. But if you've got all of those happening, then your answer is going to be 0. And every once in a while, this will be useful. It'll give you an answer when all other techniques fail. Here's an example. Imagine on your final exam, you see the integral from negative pi to pi of x cubed over 4 plus cosine x dx. And you look at that and you try to simplify. You can't, it doesn't simplify. You try to use substitution. That doesn't work. You try to use an identity. It doesn't work. As a last recourse, you could look at that function in the integrand and ask yourself, is it odd? Let's let f of x be the x cubed over 4 plus cosine x. Is it odd? If it were odd, then since we have this definite integral where the lower limit of integration is negative of the upper one, our property of odd functions would say this integral equals 0. So let's check and see if this function f of x is odd. We would have to look at f of minus x and see if we get negative f of x. And let's check it. F of minus x, if you plug the minus x in here and here, is minus x cubed plus 4 divided by 4 plus cosine minus x. And the minus x quantity cubed is negative x cubed. Cosine is an even function, so cosine minus x equals cosine of x. The minus disappears. Bring this negative out to the front, we get negative x cubed over 4 plus cosine x, and that's f of x. So we get negative f of x. So yes, this function, x cubed over 4 plus cosine x, is odd. So consequently, our property of odd functions and their integral says that the integral from negative pi to pi x cubed over 4 plus cosine x dx equals 0. So here we got an answer where all other techniques would fail. We used a property of odd functions to solve this integral. Now again, that doesn't always work, but occasionally it will, so be on the lookout for it. That's about it for today. Our summary is, if familiar integration techniques don't work, try simplifying with algebra or trig identities, or use odd functions if applicable, and take Calculus 2. We're almost done with Calculus 1. Coming up next, in Lecture 45B, our conclusion, we'll wrap this course up. So I will see you then, and goodbye.